Hi, I'm Olivia, everyone's favorite math teacher, and in today's video, we're going to talk about another application of the derivative, but specifically the tangent line. We're going to talk about linear approximations. Up to this point, we've been using the derivative to find the exact value of the rate of change of a curve at a point. But now we're saying that we're going to do an approximation instead? Well, why? What would we want to do that for? Well, we're going to do it for the exact same reason that we have approximations for pi or the square root of 2 or e. We use these values when we need to do calculations for things where we need to get a number out that we would have to use for some kind of, say, measurement, or something where using the exact value won't actually work, such as, let's say we're building a building and we don't have a ruler that has pi written on it. Or we're doing something where we only need to know pi out to, say, 4 digits. So these are examples where using a linear approximation, which is going to be a much simpler equation or a much simpler calculation, will be a lot easier. Or, for example, if we're doing something where we don't need to have quite as many cycles in a computer to do the calculation, and the linear approximation will be good enough. So it'll save us a lot of computing power. And the way this works is we remember that being able to find the slope means that we can calculate the tangent at an exact point. And when we think about a curve, the tangent at the curve is, well, kind of close enough. Because if you get close enough to a curve, it appears to be flat. That's the reason why we still have people who think the Earth is flat, even though we knew as far back as ancient Greek times that the Earth was round. In fact, they were able to calculate the size of the Earth using a stick and a shadow, knowing that the Earth was round. So, it's a little bit weird, right? So the way that we do this is we actually just use that same point slope formula that you learned back in the 8th grade, and we simply replace the y1, the m, and the x1 with our function, our derivative, and our point where we're taking our derivative. And that gives us an equation that looks complicated, but is really just the equation for a line. And then the x in this equation is going to be the value where we're taking that approximation. Now, the thing we have to remember about this, though, and the reason why we like to draw this picture, is that notice that because we're talking about a curve and a line here, the further we get from the point where we've taken our derivative, the worse our approximation will be. And that's because our line will get away from our curve. And that kind of should be what happens. So generally what we're going to need to do is decide how much error are we going to allow. And so what we're going to do next is look at an example of how we use this, and then we're going to look at how do we determine how much error we have, and is that good enough, and do we allow it? So rather than look at my bad drawings on the chalkboard, I figured we'd look at Desmos, because we've taken derivatives before, and at this point, it's better to look at the system we're looking at instead of continuing to do the derivatives. Now, if you look at the graph here, you can see what we're talking about when we say that the line and the curve can approximate each other when we're very close to the point of tangency. We're looking at a equals 2, which means we're looking at the point 2 and then f of x being the 5th root of 2, right? So that's that point right there. And so if we zoom in on that point, you see that the line is a pretty good approximation. And depending on how close we want to go, you can see that over here at 1, it's got a lot more of a gap than it does over here at 3. But right around 2, it's pretty good. So that means we could probably accept an error of as much as, 0.5, right? So that means that, we're looking here at 2 and we're going up to 3, and our approximation is pretty good. We approximated the value at being 1.26, and the actual value is 1.24. 5, which rounds to 1.26, and depending on what you needed your answer to be or how close or how much error you allowed, that might actually be a good enough value. And then if we were to say lower our value and we were to look at 2.5, we probably get an even more accurate answer. And sure enough, 1.206, 1.201. Again, very close. But if we were to go further out, like let's say we looked at 3.5, you can see that there's a noticeable gap here. And so if we go to 3.5, you can see that the error really starts to show. And so the question becomes, is this error actually calculable? And the answer is, well, yeah. So we're going to look at that next. So differentials are effectively a way of calculating the error between our approximation and our actual curve. So recall that we talked about using pi versus 3.14. Well, how do you calculate the error between using the exact value of pi and the value 3.14? Well, the problem is the decimalization of pi goes on forever. It's unending. So the error will really depend on where you go, which means the error is ultimately going to depend on the amount of error you're willing to accept in the decimalization of pi that you're using for your computation. Differentials work that same way. What we're looking at here is we basically say, what is the error that we're putting into our calculation? So what is the input error, the dx? And then from that, what would the maximum output error, so what would the dy be? So we can compare that to the delta y, which is the actual value that we would be getting from the actual curve. And the reason this can be helpful is because the dy or the delta y might be difficult to calculate, just like using the actual pi might make a calculation difficult to come out with a number that doesn't include the symbol pi. Okay? And now where this calculation comes from is, you can think of it like taking implicit differentiation to its logical conclusion, where we talked about using dy as a function of x, and so we then got y became dy, x became dx, so we talked about the change in y and the change in x. So if we treat those as individual values, and then we move them around like individual values, what we end up getting here is that the change in y is equal to the derivative of f of x times the change in x, which, because we're looking at a line, yeah, that's just like using a proportion in algebra, but now we're doing it with calculus, where we've got our tangent line, the slope of our tangent line is the derivative of our function, and then we've got the change in x being our dx, and then the resulting change in y being our dy. And so if we use that as our approximation, what we know is that the maximum error is going to be our plus or minus dy, either above or below our curve. And so because that's our maximum, we can use that in place of our delta y. And the nice thing here is that we also know that the closer we get to our point of differentiation, the closer our dy actually matches our delta y. So as long as we identify how much error we're willing to accept, and generally we do this as a percentage, we can actually determine whether or not our approximation is going to be good enough. So let's look at an example of how this gets used, and it'll make a little bit more sense to you, I hope. So here we have a machine is laser cutting circular discs out of sheet metal. The radius of the discs is 24 millimeters with an error of 0.2 millimeters. What is the maximum expected error in the disc area, and what is the percent error that this represents? Now, I've given a little bit more help before I set you on this than I usually do, in that I've gone ahead and given you kind of a hint to what you should be doing for this and a hint for what you should be doing here. Here you want to go ahead and find the derivative of the relationship between the area and the radius, and then dx is the change in the radius, and then of course that would get you the dy, which would be the change in the area. And then down here, the dy is going to be this part, which would be whatever the derivative of the relationship between the area and the radius is, and then of course the change in the radius. And then the y here is going to be the actual area you computed for that given radius. So go ahead and give this a try, and I'll show you the answer in 3, 2, 1. So how did you do? To walk you through the calculation here, we simply took the derivative of our area function, because that's how we relate the radius to the area, and then the dx here was the 0.2. That was our error. Then we got 30.16 millimeters squared was the error in our area, and that might sound like a lot from just a numeric standpoint, but when we compare it to the actual area here, we find that what we got was a difference of only 1.7%. So that means that depending on the situation, that might fall well within your error tolerance. Now, if you're looking at something that you need to have very tight tolerances for, like, I don't know, maybe you're making a laser, or maybe you're launching a satellite to an extremely distant star, so 1.7 ends up being very big as you're going, those huge distances, maybe you want to make that a little bit tighter. But, it's all going to depend on the situation. And that's one of the big takeaways for this linear approximation and differential section, is that this is a very applied aspect of calculus. And so, unlike a lot of the other things we've been looking at, here, the scenario and the situation is really going to matter when you are trying to talk about what we're doing with these approximations. So here's a couple of other examples that you can work on yourself. So I hope that overview of linear approximations and differentials helped you out. If you do have any questions about this or any problems that you're working on, feel free to drop into the comments or join us on Discord. And the answers to the exercises will be at the end of this outro. See you in the next video.